recording purposes because I am recording the lecture and the video of the lecture will be posted on the Blackboard page, which you're looking at right here. That's the Blackboard page. Sometime later today, how fast I get it uploaded. And the notes also be posted there as well. So if you miss class, then you do have this resource, right? So it'll be in this folder, class notes and videos. I'll talk more about the Blackboard page in just a minute. We really don't interact much with the Blackboard page in class here, except so you may access it depending on how frequently you're going to look at those notes and videos and stuff. But there are some things there that are useful that will be on the Blackboard page from time to time. So we much more frequently will be interacting with Webassign, which is the homework platform, rather than Blackboard. Okay. Welcome to Calculus 3. I'm Dr. Waller, and we'll look here at parts of the syllabus. Okay. And talk about how the class is going to work, but I assume everyone is ready to take Calculus 3. And so that means you guys are all smart because you all passed Calculus 2, right? Calculus 2, that's the graveyard of calculus courses. So if you've all passed Calculus 2, then I know you're all really good. So that's great. That makes Calculus 3 fun for all of us. I think the reputation of Calculus 3 and my perception is it's not as hard as Calculus 2. So you might find that a bit of a relief, okay? But now, as soon as I've said that, and if you start struggling with it, you'll be angry at me. All right. So anyway, that's the reputation that Calculus 3 has. It's certainly not as technically difficult as Calculus 2, right? So Calculus 2 has those problems, right, that go on for a page at least, right? So, trig integrals and things like that. That sort of technical level of difficulty does not show up in Calculus 3 very often, for sure. So you don't have, that's not what makes the course challenging. But what can make the course challenging is just the whole purpose of the course, which is we are going to take the concepts of calculus, right, which you learned in 2 dimensions. And then we're going to translate all of those into 3 dimensions. So Calculus 3 could maybe be better called Calculus 3D because that's what it's all about. It's taking calculus concepts and translating them into 3-dimensional space rather than just 2-dimensional space. And so the concepts of calculus are all very familiar to you. They're going to be similar, right? We do differentiation and we do integration. The sorts of things that one does in calculus, right? However, what's challenging about the course is the conceptual issues of working in 3-dimensional space, so that you're not accustomed to, because all of your math classes up to now have been focused on 2D space, right? On the rectangular coordinate system, the Cartesian coordinate system. We're still going to be using the Cartesian coordinate system, but the Cartesian coordinate system for 3 dimensions rather than 2 dimensions. And it does take a little bit of time and effort to get used to thinking in 3 dimensions. So it really does sort of test your spatial ability, okay? Your ability to conceive of things and manipulate objects in 3-dimensional space, and it's not trivial. So it takes a while to get accustomed to that, okay? And so, so at the first part, not the very first part of the course, we're still in 2 dimensions. But as soon as we switch to 3 dimensions, people start saying, "Oh, I don't feel comfortable. This is making me feel dizzy or something." I don't know. So, but you'll get past that, and and eventually get used to working in three-dimensional space. So is everyone back? Yeah. Everyone has the syllabus and the little piece of graphing paper. We're going to use that today, and then the index card. You got that? Okay. So I'm going to say other things about the syllabus, but anyway, there is the Blackboard page. So this is where the notes will be posted, right? And the videos of the class after class. And then eventually here, there will be sample tests posted here. So before we have our first test, and that's in the syllabus, I'll post sample test here for you to practice with. So practice tests. And then the test answers will be eventually posted here as well after the test. Okay, so the test solutions will be posted there. And that's primarily what's going to be going on in Blackboard. So as I mentioned, we're really not interacting with Blackboard a lot. I'm not going to post any grades in Blackboard, so there won't be any grades in Blackboard. So your grades will go into the Webassign. That's the homework platform, that grade book. Okay, and and the messages in Blackboard, you can send messages to me in Blackboard and I can reply in Blackboard, but I really strongly prefer you to not use Blackboard messaging, okay? Because I don't look at it that frequently, and it doesn't send me a copy of your message to my regular email. I have to actually physically log on to Blackboard and look for messages. So I miss messages this way. So don't send me, try to avoid sending me messages through Blackboard. You can message me through Webassign, or better yet, you can just email me to my university email address, okay? So that's the easiest way to communicate with me. So don't try to avoid messaging me through Blackboard. So if you're accustomed to doing that, sorry. Let's try to do something else. Let me look at the syllabus is here. So let me open that. I think I got the link working right. So, all right, so there it is. So this is what I gave you on a paper, right? I just want to hit the highlights here. Important things that we need to know from the syllabus, and then other things we might come back and refer to later. So there's a description of what the course is all about. That's sort of what I just told you there, right? Okay. The learning outcomes, those are just required on any sort of syllabus. Here is the book. So the book is called Calculus, not surprisingly, by these authors, Larson and Edwards, but I think it's the 12th edition. However, you don't have to purchase a physical copy of the book, right? Because you're going to get an e-copy of the book with the homework platform. All right. So when you purchase, but you will have to purchase access to Webassign, which is the homework platform, then you get an e-copy of the book. So that's more than sufficient. I probably will not be referring to the book, that sometimes maybe referring to pages from the book in class, but I won't be assigning, readings from the book or anything like that. Most of the material for the course will be presented to you in the form of notes, right? That I write. So our interaction with the text itself will be limited, except for, of course, the homework problems that come from the text. All right, but those also live in the online homework platform, right? So you won't be looking homework problems up in the text for any reason. So so the cost there here of the text, which includes access to Webassign, is about $100. That's online, right? Okay, because that's all you need. You don't need a physical copy of it. And so I think it's like 100 if you just buy a single semester access, right? Which is all you need. So look, when I'll show you here in a moment, but when you're registering for Webassign, right? That is when you purchase access to Webassign, that's when you get access to the book, right? The electronic copy of the book. Now, they are going to try to sell you different versions of the book, okay? But you don't need any of those different versions. You just want single semester access. This is Calculus 3, so you're not going to use this book. There's no Calculus 4. So this, no reason to use this book again. So so you just want the single semester access, right, to the text. But they're going to try to present you these other options, so you don't need those other options, right? Okay, so don't spend more money than you need to on that. I'll show you Webassign in just a second. Okay, so let's skip through all of that. I'll show you the access to Webassign. There's information about the Math Center. I'll say more about the Math Center. That's the tutoring center. I'll say more about that later on. Because I will be in the Math Center on Mondays and Wednesdays afternoon after class from 2 to 5. So that's if you need to see me and meet with me, then that's where you'll go. Okay. Now, here's kind of the classroom policies part of the syllabus. So this stuff, of course, is kind of important. So let me at least say it there. I will take attendance, probably starting as early as next time. So I will take attendance, and it's just an attendance sheet that you sign. So there is an attendance policy, and so the policy is that you don't want to miss more than 4 classes. So I would prefer that you not miss any, but you don't want to miss more than 4 because then you're in violation of the attendance policy. Okay, so you all right, so you'll have to look a little bit later in the syllabus to see what happens if you violate the attendance policy. All right, you're not going to be like physically punished for that, but there's a slight penalty here for violating the attendance policy. So please try not to violate the attendance policy, right? It's important that you're in class because we're going to be doing a lot of things in class. Now, however, as I mentioned, right, I'm taking the lecture. So if if it's inevitable that you cannot come to class, then you can always look at the tapes, right? Okay, so you have that backup. You can also look at the tapes just to review things as well, if you want to, of course. We do have tests, so we're going to have 3 regular tests. They're just written tests. And as I mentioned, you'll have sample tests for those, so you will have knowledge of what the tests are going to, sort of look like before you take the test. So you're not surprised by the sorts of questions that are on the test. They'll be very similar to the homework problems, though. But we do have 3 tests, and then we have a final exam. And I forgot, we'll have to look at the percentages, but the final exam is probably 25%, and the 3 tests are probably, let's count this right. Can't be 15%, because that's not going to work, right? Let's see, what are each of the 3 tests? Does it say there? Oh, 20% each, okay, and then the final exam is 25%. So there'll be a written final exam at the end of the semester in the final exam period, just like it'll be like the 3 tests, right? And then homework is 15% of your grade. Okay, so that all adds up to, I hope that all adds up to 100%. So each of the tests is 20%. So we have tests, right? So you don't want to miss the test, of course, but if you do miss the test, please make sure that you let me know as soon as possible, preferably before class, that you're going to miss a test. But if you don't contact me pretty quickly after the test, then there won't be any sort of makeup provision. So you'll just get a 0 for the test. So be careful about that. No, you guys are all experienced college students, so I'm not going to have, I know I'm not going to have this issue with you, but I teach freshman classes as well, and they do strange things when they miss tests. So, but I know you won't. We do have homeworks, right? They'll have regular due dates. We have this online homework system for which you're paying, which is a really crucial part of the class. Because it's by doing the homework that you'll be preparing for the test. And then, of course, preparing for the test is how you do well on the test. And that's how you make a high grade in the class. But we do have regular due dates. There is, however, there is possible to turn in homeworks late. So there's a penalty that happens when you do that, when you turn in homework, when you work on assignments after the due date. there's a penalty, but it's not that bad of a penalty. So it is worthwhile definitely to continue working on homework problems after the due date. But of course, you want to get as much done before the due date as possible, so you don't have to pay any sort of penalty for those. I don't know when our first due date is. We'll look at Webassign here in a moment and see. I think it's August 31st. What day is August 31st? Is that a week from? Is that Wednesday? Next Wednesday? A week from Wednesday? Am I counting right? Yeah, I think it is, right? So you have your first assignment would be due on not this Wednesday, but the week after that. So something due that's going into the Labor Day holiday. So we have Labor Day off here. That's not because we have a Monday class. So that's nice. And you can now immediately enroll in Webassign even without paying. So you have a grace period. So we can immediately start working on the homework. So you'll be able to hit that due date without an issue there. Try to put your cell phones away during class, or just put them away so you're not looking at your cell phone while you're in class, because sometimes I go crazy when that happens. So try to avoid that, right? Okay, we have a now. All right, so I think I'll save this for later because this is going to get a little bit tedious to go through. But we have a very elaborate extra credit system. So this is called capital sports. So it is possible by doing things like doing well on your tests, which you well by studying for the test, right? So if you do well on your tests, keep your homework average high, you will earn what are called flux dollars. So these are like extra credit points for the end of the semester. And then at the end of the semester, you can use those to purchase things like you can buy your way completely out of the final if you have enough flux dollars. So if you have enough flux dollars, you don't have to take the final exam. Or you can also buy extra points on your midterm. So you can buy bonus points on your midterm at the end of the semester if you want to improve midterm test scores, right? Okay. So there are lots of ways to earn flux dollars. And so you can see the list here. I think when we get a little bit here further into the class, we'll talk more about earning flux dollars and spending flux dollars. You can also earn flux dollars for not violating the attendance policy. Okay. So see, if you don't violate the attendance policy, you can earn 25 flux dollars. And those $25 will come in really handy at the end of the semester. Trust me, you're going to want those $25. So it's definitely beneficial, not only just for your own edification, but in terms of extra credit, definitely beneficial to not violate the attendance policy, right? Okay. Okay. So maybe when we get closer to the first test, we'll look more at the good things you can do with your flux dollars. One way to earn flux dollars is to visit tutoring sessions outside of class. So you can do that in the Math Center. And as I mentioned, I'm in the Math Center 2 to 5 on Mondays and Wednesdays. So if you come visit me in the Math Center on Mondays and Wednesdays, you can earn flux dollars that way, okay, as well. $2, it's only $2 per week, all right? So you can't be just going to the Math Center constantly, although that would be great for earning flux dollars, all right? Okay, but you can earn flux dollars that way. Okay, here's the schedule for the semester. So we have our first test on September 21st, so you can sort of be thinking about that, okay? That's when our first test will be, and we'll probably stick pretty closely to the test schedule here. And second test on October 26th and the last one on December 5th. And then I don't know when the final exam is. So it'll be like something like a week after December 5th, though, right? Because they haven't announced the final exam schedule. Okay. So I can't show you that yet. Y'all have any questions there about things in the syllabus so far? Oh, that really gets boring to go over, but some of the things we have to say. So you've got a paper copy of the syllabus, and then the syllabus is posted in Blackboard, right? So you can find it. You can always find it in Blackboard. Okay. Let me tell you about what we're going to do with the index card. So take the index card, and all you need to do is fold that This is called hamburger style. So you fold it hamburger style. These are really small index cards, so I couldn't find the big ones. I have some bigger ones, but I couldn't find them. So you fold like this, right? Not like this. That's hot dog style. Like this is hamburger style. So you fold it like that just to make a tent. And then, because I want you to write your name on one side of it, right? So you put it right. So I learn everybody's name. And I'm not, I don't hate. I don't like to say hate you. So put your first name and your last name, but the name you want me to. So just write that for me. So that when we're doing things in class, I can see your card. I can, which is an issue too. Did I give you one? Okay. Okay, so just put that card in front of you, where I can see it, and you don't have to take it with you. I'll collect them after class, and I'll keep track of them for you. Okay, and then after a little while, I'll know everybody's name, and then we won't have to. At some point, we won't have to deal with having the name tents. Okay, also helps your classmates too. Maybe remember who you are as well. Okay. All right. Let's look here at questions right now. Let's look at Webassign here because briefly, because I do want you to get registered. Well, okay, there's two parts to Webassign. I want you to get enrolled in the class, so you're on my roster in Webassign. And then actually registering for Webassign is when you pay for it, and you don't have to do that immediately. Okay, so you've got a 2-week grace period. So I think you can continue using Webassign until like Labor Day, right? Okay, because that's 2 weeks from today. So that'll be through the first maybe homework assignment or two. You can finish, those before you actually have to purchase Webassign. So if it's if it's going to take time for you to collect the funds to purchase Webassign, you've got a grace period here, right? Okay, to do that. I noticed some people are already enrolled. That's great. All right, so let me show you how this works. So well, just a little tiny bit of it because I can't do the whole process. But you go to webassign.net, so it's .net. There may be other ways to access it. There probably are. All right, and then so at webassign.net, one of the things it's going to ask you is to enter your class key. All right, so that's what you do. Just enter the class key. And that's in the syllabus. So if you look on the syllabus under that part that's discussing Webassign, which doesn't say Webassign, I think it's on page 4. Yeah, it's on page 4 right here where it's bolded. That is the class key. Let me see if I can type that in. So let's see what happens when we do that. So it's UHD. Do I need the space there? I don't know. UHD, what else is it? Can you tell me? 1318. 1318. And then what? 3892. Let's see what happens. Okay, so that looks promising because that is the right thing. And that's me. So I think that'll get you to the right spot, right? Okay. Now, you may already have a Webassign account. And if you have a Webassign account already, you can use the same username and password. But you still have to purchase access at some point eventually, right, to this book, right? But not immediately, right? You still got, I think, a couple of weeks here. As a grace period. Okay, I don't want to continue this process because it's going to start asking me to, either sign in or create a a username and password to sign in with, right? So if you've already got a Webassign and username and password, then you can use that. The I hope that the email that's associated with your account, well, maybe we don't always need to turn that back on. All right, so the email that's associated with your Webassign account, I hope it's an email that you're actually looking at, because I send a lot of messages through Webassign and they go to that email. So try to use an email that you read. So it could be your Gator mail, that's fine. But I'm not really a sticker for using Gator mail. So if you want to use some other mail, Gmail or something, that's fine. Just use whatever email you want to. Okay. But keep in mind, I do send messages to that email. All right. So actually pretty frequent. So an email that you read would be useful to have it in a website. I don't know how easy it is to change your email settings, once you've already got a Webassign account. I never tried to do that before, so I don't know if that's easy to do or not. All right, let me click out of this, and let me try actually now. Let's try actually looking at Webassign. Let me try signing in. So when you sign in, of course, my account's going to look a little bit different, but let me go to the student view. So when you sign in, once you're registered for the class, I think you'll get something that looks roughly like this. So probably when I start class each day, this is what will be showing on the screen, just as a reminder of what our homework assignments are. And we already have a homework assignment on this topic called vectors, which are a tool we're going to use to help us translate these calculus concepts to 3 dimensions, right? Okay, and they're important mathematical objects in their own right, apart from calculus. So that's the first topic that we're going to take up. You may be familiar with this topic from some other math courses that you've taken, so that would be good. But if you don't, we're taking it from scratch, so you don't have to have any familiarity with vectors at all. Notice that these are going to be vectors in the plane, however. So we're still, for the time being, restricted to, at least initially here, to 2 dimensions. But notice in the very next homework assignment, it says space coordinates and vectors in space. That means 3-dimensional space, right? So we're going to be switching to 3D space pretty quickly. Okay. All right. So anyway, there's the very first assignment. So you can start working on that. That's due on August 31st. So we should have enough under our belt today, if I ever shut up, enough under our belts to where you can start working on this. And this is where your grade will be kept, right? So you'll see your current average here in Webassign. This is not going to have much meaning until our first test, but it's there. It'll have your homework average until the first test, and then after the first test, then it'll have more significance to it. But that's where your average is, and here are where I put announcements. So our announcements for the time being, are pretty dry. There's just where my office hours are going to be in 925 North. That's the Math Center, right, from 2 to 5. What I already told you, right? The lecture notes and the videos are posted on Blackboard, right? And then there's a description of how you can get an extension for due dates in the homework, right? So there's an announcement there. So if you're running past, if you haven't finished your homework by the time of the due date, here's how you request an extension, but you get it automatically. So that's easy. I don't have to approve it. You get that automatically. Okay, so that's what Webassign will look like for you once you are properly enrolled. If you have trouble enrolling, of course, just you can email me, or you can ask me next time in class, right? If you're having issues. Here at the beginning of the semester, everyone is starting school at the same time, particularly next week. It's going to be busy, or Labor Day week is going to be busy. So at those times, Webassign can get slow. Usually it's really fast, but Everybody is logging on, trying to create an account simultaneously here in the first couple weeks of the semester. Sometimes Webassign can, that's when it tends to be glitchy if it's going to be glitchy. So if you run into some glitches, you may expect that, but let me know. Okay. Have y'all used Webassign before? So if you took Calculus 2 here, you probably used Webassign before. All right, so y'all are pros with Webassign. So most of you. So it's once we get through some notes, maybe next time we'll open the homework, and I'll show you, for those who are novices, just a little bit about how you enter your answers here in Webassign. But it's all very it's pretty straightforward. Okay, I think. All right. If you've used another homework system, probably almost all of you have used some sort of math homework system. They're all very similar to one another. Okay. All right. Let's stop there and switch. So I'm finally through talking about sort of just class policies, and we're actually ready to get into some of the guts of the material. Okay, because so we are going to do lecture today, and we're going to do a little bit of hands-on stuff. So that's what the graph paper is for. So if we're not through all of our hands-on stuff, hang on to the graph paper, right? Hang on to the graph paper for next time. Let me switch to the notes now, and let's get started. But we are going to take a break here in a minute. It's hard to get through this full hour and 45 minutes without taking a little bit of a stop, especially for me, because this math gets a little bit tiresome after a while. So I need a chance to breathe. So here are the notes. So this is what will be posted on Blackboard, right? Okay. These are the blank notes, but I'm going to start filling them in. And I will post those then. Some people ask me, can I post the notes before class? And I'd love to be able to do that, but that's hard for me to do because I'm not always quite sure where I'm going to be in the notes on any particular day. So you may have to wait till after class to get a copy of the notes if you want to download a copy of the notes. Okay. All right. So as promised there, we're going to be talking about vectors in the plane today. And from the text, if you are interested in looking at the text and reading from the text, that is chapter 11, section 1. Okay, so you can go and look at the author's discussion of vectors in the plane, which of course will be quite similar to what I have here, right? But anyway, that's where we are in the text. So this is pretty straightforward to begin with, okay? Because again, as I mentioned at first here, we're working in 2D space. And so in two-dimensional space, in the plane or the rectangular coordinate system, vectors are not really that difficult to think about, okay? Sometimes their applications are a little bit tricky, and the book doesn't the applications are tricky sometimes because frequently they come from physics, and the author really doesn't explain the physics very well. So you sometimes have to read the example to understand how the vectors are being applied in some physics problem. Okay, he just said, well, we can use these two vectors, and here's what you do with the vectors. And he doesn't really give a very good sort of conceptual explanation of why you can do what you're doing with the vectors. But we just have to take him at his word. Okay, so most of the quantities, right, we work with in practical applications, you can measure those with a single real number, right? Okay, so quantities like area, right, area of a surface, or volume of a three-dimensional object, or mass of an object, right? Okay, or time and distance. Those quantities that we frequently deal with in mathematics, we can measure those with just a real number, right? Okay, so just a single real number, and that's all we need to measure the quantity. So quantities that you can measure just with a single number, these are called scalar. We're going to refer to these as scalar quantities, right? So now you may have never heard the term scalar before. And because we've never really needed that up until now, okay, in our mathematical training. But there are frequently quantities in applications that cannot be measured just with a single number. So these quantities are a little bit more complex, okay? So quantities like force and velocity, all right, those are a little bit more difficult to work with because they often involve some amount that you're measuring, but they often also involve direction, okay? So force is applied in a particular direction. Of course, force, there's an amount of force that's applied, but force is applied in a direction, all right? So sort of wrapped up into that idea of force is both some numerical measurement, some quantity, the amount of the force, but then also the direction of the force as well, okay? Same thing for sometimes for velocity. You have, of course, the speed of an object, right? Its velocity, but you may also want to work with the direction of the object as well, right? Not just its speed in a right, but the direction also in which it is traveling, okay? And so scalars, right? Scalar measurements are not appropriate, right? To help us with things like to always help us with things like force or velocity, all right? So that's where the idea of vector comes into play, okay? So vector encompasses two measurements, okay? Some amount that's being measured, all right? That's called usually the magnitude of the vector, and then also the direction, all right? So vectors also incorporate the idea of direction. What do vectors look like then? Well, a good way of representing a vector, right, at least when you're starting, is by drawing a picture of a vector. So we think of vectors as being directed line segments, okay? So when you're writing down a vector, one way you can write it down on paper is by drawing a directed line segment. So here is a picture of a vector, okay? So now this is a two-dimensional vector. So this vector exists in 2 dimensions. So notice this vector has an initial point, okay, and then also a terminal point as well. Now, so how is it that that line segment now incorporates these two ideas that I mentioned, right? Because vectors have a quantity associated with them called the magnitude of the vector, but they also have direction as well, all right? Well, you can sort of see how the direction is implied, right? Okay, in the picture, because this is a directed line segment, right? So it's pretty clear, right, that the direction of this vector is from the initial point to the terminal point, correct, right? Okay, so, but it's very important to remember vectors have initial points and terminal points, okay? And the initial point and terminal point are not interchangeable, because if you interchange them, you're changing the direction of the vector, and that's an important part of the vector is its direction, okay? So here, if I interchange the terminal point and the initial point, I get a different picture, right? The directed line segment is going this way, and that's a different vector, okay, because it has a different direction. So you can sort of see how the direction here is sort of implied by this picture that we've drawn of the vector. But what about the magnitude of the vector? So where does that come into play in this picture, right? So how does this picture express magnitude? Well, that has to do with the length of the vector, okay? So it's the length of this vector, the length of this directed line segment that incorporates the idea of the magnitude of the vector, which is the second important measurement, right, that vectors are supposed to incorporate. Okay. Let's see now if we can figure out then for this vector. Oh, by the way, this vector is called U, so we often use lowercase letters like U and V and W are our favorites, X, Y, and Z, to represent vectors. And in the book will make them bold, so you can understand that that is a vector. And sometimes to just really make that emphatic, the book will put a little arrow above the letter, just to make it clear to you that definitely is a vector. But it gets a little bit cumbersome to keep writing down those arrows, so we often drop those after a while. Okay, and we just use the bold lettering. Okay, we're going to be working with vectors a lot, so many of the expressions that we write down here in class will involve vectors, and you'll get very skilled at understanding when a letter is representing a vector and when it's not. Although sometimes it's still ambiguous. Okay. All right. So let's see now if we can. Let's see by looking at this picture of this vector. Oh, by the way, its initial point here in the plane is its initial point is what here? What is that point? Can we count that? Is that -1 and 4? Is that right? -1 and 4. And then the terminal point here, what does that look like? 1, 2, 3, 4, 5, 6, 7, 8, -8. Am I counting right? And 2? Okay. All right. So initial point -1 and 4, terminal point -8 and 2. All right. So let's see now if we can calculate these important measurements that are associated with vectors, right? Namely, its magnitude and its direction. So I said it's the length of the vector that sort of incorporates the magnitude of the vector. So if we want to compute the magnitude of this vector, what we would do is compute the length of this directed line segment that I've drawn here, right? Okay. And how do you compute the length of a line segment like this? What formula do you use? Yeah, use the distance formula. Sure, right. Yeah, you use the distance formula. So we know how to compute the magnitude of a vector. We just use the distance formula to compute the distance between the initial point and the terminal point, right? By the way we indicate the magnitude of a vector symbolically on paper is we use double vertical lines. So it's sort of like double absolute value bars here. So put that around the name of the vector, and that indicates the magnitude. That indicates the magnitude of the vector. So y'all told me let's use the distance formula. So remember, in the distance formula, you take the square root of the sum of some squares, right? And the squares that you're summing up under the square root, you find those by taking the difference in the coordinates, right? So you take -1 minus a -8. Am I doing that right? -1 minus a -8, and you square that. And then also you add in what? 4 minus 2, and you square that, right? And add those two squares and then take the square root. And that should give you the distance between the initial point and the terminal point. That's the magnitude of the vector. Let's see if I do these calculations right. What do I get? Oh, let me lower the screen here. I don't have to. Let me lower the screen here so I don't have to be bending over. Okay. So let's see. What was this? -1 minus a -8. So that's -1 plus 8. Is that 7? So I have 7 squared, and then plus this is obviously 2 squared, right? So that looks like the square root of 49 plus 4. Is that 53? So 53 is probably a prime number, right? So I can't really, is it? I think so. I can't simplify that square root though very easily by hand. So we'll just have to leave it as square root of 53. Okay. That's a little bit more than 7, right? Somebody have a calculator? 7.28. Yeah, approximately. Okay, so there's the magnitude of the vector. That's pretty easy to understand, right? So if you were to extend this vector by moving this terminal point a little bit, okay, then you're going to get a longer line segment, right? So you get a greater magnitude. But notice you would still have the same direction. You would still have the same direction. Or if you shorten the vector a little bit, right, you get a lesser magnitude, right? But you still have the same direction, So all of these vectors that I've drawn here, here's 3 of them, they have different magnitudes, but they all have the same direction. All right, let's see now. So how then will we measure direction? So do you have any ideas of how we could measure the direction? I mean, I can see it there, right? But is there a way that I can quantify the direction? Do you have anything from your mathematical background that would allow you to quantify here? 360. Yeah, okay, so your idea is really sort of spot on. Okay. I was thinking of something simpler. Okay. So yes, to begin with here, because this is a line segment, right? And so I was thinking of slope, okay, because that's easy to calculate. And I don't have to think of any trigonometry. Right? So that was my idea. But we're going to see this idea is not really very good. It's not really perfect. Okay. I can, however, calculate the slope of this line segment. Okay. So when we calculate the slope of this line segment, let's see, what would we get? So how do you do that? You take the difference in the y coordinates, right? And you divide it by the difference in the x coordinates. Is that right? Did I already do that though up here? So is it 4 minus 2? That's 2, right? And then minus 1 minus a minus 8, that's 7. So then I would get 2 over 7 as the slope of this vector, right? Okay. So that was kind of my first thought of how to attach a number to the direction of the vector, without getting too fancy, is to use the idea of slope. And so we come up with the 2/7. So you might say, oh, the direction of this vector is 2/7, okay? Because that's the slope of the line segment that I've drawn, okay? However, that unfortunately is not sufficient, okay? Because slope is directionless. So if you calculate the slope of the vector going in the opposite direction, right? Okay, that's a different. So if you had initial point here and terminal point here, that is a different vector, clearly, because the direction is completely opposite, right? But if you calculate the slope again, you will get also 2/7. Okay, remember, when you calculate the slope between any 2 points, the slope from point A to point B is going to come out as the same as the slope from point B to point A. All right. So these 2 vectors that clearly are not meant to have the same direction, if you calculate their slope, you'll still come up with 2/7. So the moral of the story is their slope is not the appropriate way of measuring the direction for a vector. It's not quite good enough. All right. So it's a good place to start, but it doesn't quite fit the bill. So we're not going to use slope to sort of answer this question: what is the direction of a vector? How do we measure the direction of a vector? We cannot use slope. Okay, doesn't quite work. So we are going to have to move on ultimately to something more sophisticated. Okay, all right. But we're not there yet, so we're going to save that problem for a little bit later. Okay. Now, another thing that's and this seems like very simple when I say it, but this takes a while to get your mind around, okay? Because it's just different from the two-dimensional mathematics that you've done up until now. Vector has direction and it has magnitude, but it does not have position. Okay, position is not part of vector. So, and this is sometimes very troubling for students. So if you take this, let me see if I can do it. If you take this vector, the original vector that I called U here, see if I can do this. Let me see if I can do this. Now, you have to do it part of just, yeah, no, okay, I'm just gonna draw it, all right? So if you take that same vector and just copy it, right, elsewhere in the plane, you get it, you've got the same vector. It's not a different vector. So, so if I draw here, if I draw here this vector and I call it W, and I say, okay, I have a new vector here, W. U and W are really the same. They're really the same vector. Because, again, what's important in vector is magnitude. Well, these two vectors have the same magnitude, right? Okay. And direction. But these two vectors have the same direction. So therefore, these two vectors are really equivalent to each other. All right. Now, you might say, but they can't be because they don't have the same initial point and they don't have the same terminal point. The initial point and the terminal point are just there to help us draw a picture of the vector, but they're not fundamental to the vector. Okay. So these two vectors really are same vector. Okay. Because they have the same direction and the same magnitude. Right. So you could position that same picture anywhere here in the plane, and you would get would have the same vector, right? So just keep that in mind. Position is not important to vector, okay? The same vector can have different positions and still be the same vector. Okay. So how do we represent vectors? Well, you already saw one way, of course, is to just draw a picture of the vector, right? So here's a couple of vectors that I've drawn pictures of, and you immediately are thinking those two vectors are really what? I think they're really identical, right? Okay, I think those are really the same vector, right? So we're fooled into thinking those are different vectors, but really the same vector, okay? Because I think they have the same magnitude, they both have the same direction, right? But anyway, to represent vector on paper, right? One way is draw a picture of the vector, okay? But we can't always be drawing pictures, right? Because that's a little bit clumsy. So we need a little bit more efficient ways of drawing vectors. So one thing you can do, instead of drawing the picture, you don't have to have the picture, you can imagine the picture. So one thing you can do instead of drawing the picture is just write down initial and terminal point, right? Okay, because if you've got the initial and the terminal point, then you can create the picture yourself, right, easily. So so here's another way of writing down vector, is just to write down the initial point and the terminal point. Let's see, is that the right? Did I write down the right initial and terminal point? Let's see, 2 and 5. Yeah, that's right. And this is what? Um, 1, 2, 3, 4, 5, and 1. So for U here, did I get the right initial point and terminal point? Yeah. Okay. So there's another way of writing down the vector U, right? It's essentially the same as drawing it though, because you can recreate the picture here. You can recreate the picture here really fast, right? Okay. From the initial point and the terminal point. Now, just to make clear that this is a vector, we're going to put it in these pointy braces though. And so we really kind of are going to reserve these pointy braces for vectors here in the course. So when you see pointy braces like this, you should be thinking vectors. So you can draw a picture of a vector, or you can just write down its initial and terminal points, right? But again, the problem with this is, as I mentioned, that this vector v appears to be different because it has different initial and terminal points. So this vector v looks like it's a different vector because the initial point and the terminal point are different, right, than they appear to be for u, but these are really the same vector. So u and v are really equal to each other, even though they appear to be different. Because they're equal to each other because why? They have the same what? Yeah, direction and magnitude, right. Yeah, okay. That's what's important with vectors. It's not their position. Okay, so although their initial and terminal points are different, these really are the same vectors. All right, so one way we can help overcome this problem is we can assume, all right, we can assume that all vectors have as their initial point the origin, 0, 0, okay? And if we assume that all vectors have 0, 0 as their initial point, right, then that means the terminal point is all that's really important here, correct? Okay, so you can also indicate a vector if you assume that its initial point is 0, 0. You can also indicate a vector just by writing down its terminal point, okay? And so if you assume that a vector has its initial point 0, 0, this is called the component form of the vector, okay? Let's take these vectors v and u, and let's translate them so that the initial point is 0, 0, okay? So we're just going to move them so that the initial point is 0, 0, and then that will allow us to write down the component form of the vector, because in the component form of the vector, all you do is write down the terminal point. You're assuming that the initial point is 0, 0. Let's see, let's try it here. Let me see again now and see if I can make it work this time. There I captured it. So let's copy that, and then let's paste it. Did it paste? Maybe. And let's see if I can get it at the origin. All right, so there's the initial point there at the origin. So when the initial point is at the origin, right, 0, 0, then what's the terminal point? Looks like what? What is that? 1, 2, 3, and then -4, right? So the terminal point there becomes 3 and -4. And then your representation for the vector, all you have to do is write down the terminal point. But again, we're going to enclose it in pointy brackets. And we're not going to use parentheses either. So we can also write the vector u like this, okay? So that's called the component form representation. What is the other? What's the lengthier representation if you write down both of the initial point and the terminal point? Let's see, what was that? 2 and 5, right? And what's this? 1, 2, 3, 4, 5 and 1. Am I doing that right? So that's kind of the lengthy representation of the vector where you write down the initial and the terminal point. But here just write down the terminal point, assuming that the initial point is 0, 0. Now, the advantage this has is that it's shorter for one thing, right? Okay, but you don't have this pesky problem of different vectors having of the same vector having different representations. So let's see, what's the vector v look like if we're going to write down the initial point and the terminal point? Let's see, what's the initial point here? -7 and 6. Am I counting right? And then this is what, -4 and 2. So you see, there's what the vector v looks like if you write down the initial point and the terminal point. So see, it looks completely different from u. But if you take v and translate that to component form, like we did u, you get exactly the same thing, right? Okay, you get 3 and -4. In other words, if you take the vector v and just copy it, see if we can copy it, just like we did u, right? We take it and copy it here. So its initial point is at the origin. See, you get exactly the same thing as v, right? Okay. And its terminal point then becomes 3 and -4. So most of the time, we're going to be writing vectors down in component form, right? Not always, but a lot of the time we'll be writing them down just in component form, just assuming that the initial point is 0, 0, and then all we do is write down the terminal point of the vector to represent the vector. All of that is just summarized here in all of that summarized in this paragraph. Okay. So if you have a vector, right, here's a vector. Here's a picture of a vector with its initial point at P1, P2, and here's its terminal point at Q1, Q2, right? If you want to convert that to component form, so in other words, if you want to translate that vector so that the initial point is the origin, then that's really easy to do, right? All you do is take the difference in the x coordinates, right? Take the difference in the y coordinates, correct? Okay, and that will give you the component form of the vector. Just again, take the difference in the x coordinates, right? Take the difference in the y coordinates. That will give you the component form of the vector. And then the magnitude is really, when a vector is in component form, the magnitude is really easy to measure. All you have to do is take the squares of the two components, right? And then take the square root of that, and that gives you the magnitude. So it's real easy to compute the magnitude. Of course, you can have a vector that has no magnitude and no direction. That's called the zero vector, and that's what it looks like in component form. So 0, 0 is a vector, not a very interesting one, but it is a vector. It has no direction and no magnitude, right? Okay, so its magnitude is 0. All right. All right, let me give you all one to practice with so we can take a little bit of a breather here. So you can do this on your graph paper, right? So easy here. Just draw that vector for me, v. There's its initial point, and there's its terminal point. So draw a picture of that for me. But then what I want you to do with it is put that in component form. So what does that vector look like in component form? And then what's the magnitude of the vector, right? But also draw me a picture of it. So in written form, the vector would look like this. Right? So you're going to draw a picture of that vector here. But I want you to write it down in component form. So what does it look like in component form, where you just have two numbers here? And then what's the magnitude? Okay. So just compute the magnitude for me. Very simply. It's up to you. However you want to respond. Okay, let me turn the lights back. So stay on. I'm not grading these, so I'm not grading these, so up to aim for. right here. Components. But the second one are easier. You have to do the same. But again, that's the so, so did y'all make some progress there? I think most people are almost done with it. So let's take a look at what it looks like. So it's pretty easy to draw the vector, right? When you've got the initial point and the terminal point, right? Okay. So your initial point is what? 3 and minus. Let's see if I can see if I've got enough space here. Let's see. So your initial point is 3 and minus 7. So down here, right? And then the terminal point minus 2 and 5 up there, right? And then you just connect those with a directed line segment, right? So something like this is what that vector looks like, okay? But again, we can translate that. We can shift that all over the plane, right? And have exactly the same vector. So to get a better idea of what the vector really is, we just put it in component form, right? We assume that this initial point has been translated up to 0, 0. So you do that by, remember, take the terminal point x coordinate and subtract off the initial point's x coordinate, okay? So so we would have minus 2 minus 3 is going to be the first coordinate in component form. And then same thing, take the for the y coordinates, take the terminal point y coordinate and subtract off the initial point y coordinate. I don't think I emphasized that enough a moment ago, right? So take 5 minus a minus 7. So you end up with what? Minus 5 and 12 as the component form for the vector. And you don't need to write the parentheses here. Just put the pointy brackets. And now the magnitude is really easy to compute because in component form, to compute the magnitude of the vector, which we denote by those double vertical bars, those double absolute value bars, just take the squares of the two components, right? And then add those together and then take the square root. So you have minus 5 squared plus 12 squared. Square root of that, that's the square root of 169. And 169 happens to be a perfect square. How convenient. That's the square of 13. So that does simplify. And so we just get 13. Is that what y'all got? 13 for the magnitude, and then minus 5 and 12 in component form. So what does that thing look like in component form? So we assume that it begins here, right? And the terminal point is 1, 2, 3, 4, minus 5. Is that minus 5? 1, 2, or 5. And then, oh Lord, 12. I don't know if I can get up that high. 1, 2, 5, 6, 7, 12. Oh, way up here. hard to see that vector because it's going to overlap itself, right, for a little bit. So there's the vector drawn in component form, but still the same vector, right? Because same direction, same direction, and same magnitude. So that was the second question there. Now, now that we have vectors, though, are mathematical objects, right? Vectors are mathematical objects, and like numbers, all right, we just have different purposes for them. But we need to be able to do the same operations with vectors that we do with numbers, okay? So what sort of things do we do with numbers? We add them. Yeah, that's one of the very first things that you think of, right? Is that we add them together, all right? So so we need to learn how to add vectors together, okay? The other thing that we're going to learn how to do there is how to multiply a vector times a scalar. So remember, scalar is just a single number, right? Okay, vector is a little bit more complicated thing, but we can take scalars and multiply them by vectors. All right, so let me show you how to do that. That's really simple. But first, let me show you how to add vectors together. So I have a picture here of a couple of vectors, okay? And so U and V. And so what I want to see if I can draw a picture of is U plus V, all right? So if you add U and V together, of course, when you add U and V together, you want to end up with another vector, right? You want to end up with another vector. So hopefully when I add these two things together, I'll end up with another vector. The idea here is very simple, though, okay? What you're going to do is just sort of lay these vectors end to end, all right? So if you're going to take U plus V, right, here's U, and now use the end of U as the initial point for V, okay? So in other words, I'm going to move V, and remember, V has no position, so I can move it anywhere. So I'm going to move it up here so that its initial point is the terminal point of U. So if I do that, what would that picture look like? Here, we better see what is V in component form. Maybe I need to draw that. Maybe I need to write that down. What's the component form of V? See, I can write down easily the component form of V because its initial point is the origin, right? So it's what, 1, 2, 3, 4, right? Is the X coordinate in component form, and 2 is the Y coordinate. So there's what V looks like there, right? 4, 2. But I'm going to translate V so that its initial point is the terminal point of U. So to draw a picture of that, we'll just start here at the terminal point of U. Let's see, go over to the left 4 units, right? And go up 2 units because that's what the component form of V says, right? So you get a picture like this. So there is V. And now when you add U and V together, the new vector you're going to get is just this vector, okay? There is U plus V. Start with the initial point of U and end at the terminal point of V. That would be the vector that is U plus V. That's how we add vectors together. When you add vectors together now, what you get there is called, of course, when you add numbers together, what is the result that you get called? Sum, right? Okay. When you add vectors together, well, you get the sum of the vectors, but the other term for that is the resultant. Okay, that's a term from physics, but we use it frequently. So the resultant vector U plus V. Here's what it looks like. By the way, it's easy now to write down the component form of U plus V, right? because we can count off here very easily. Let's see. Notice, see, the initial point of u is still zero, of u plus v is still 0, 0, right? So the terminal point would be 1, 2, 3, 4, 5. Is it 6 there? Right? And the on the x-axis, and then on the y-axis, 1, 2, 3, 4, 5, 6, 7. So there's the component form of the resultant vector. It's just 6, 7. By the way, it's very easy to see how that came about. All you did is add the components of u and v together, okay? And that gives you the sum. Nice to draw a picture of that. Here's my question, though. Here's my question. Do vectors work like scalars? You know, in scalar arithmetic, the order in which you write the terms down, the order in which you add two numbers together is irrelevant, right? For scalars, u plus v and v plus u are the same, right? They give you the same answer. Is that also true for vectors, though? So is u plus v, is that going to turn out the same as v plus u? Well, let's see. How would v plus u work? We would start with v first, and then what would we add on here? At the end of v, we would add on the vector u, right? Let's see. What is the component form of the vector u? The original vector u. Let's see. That went, what, 2 on the x-axis, right? And how many on the y-axis? 5? So the component form is 2 and 5, right? So I start here at the end of v, go to the right 2, and go up 5, and oh, that's nice. Puts me right there. And so what's the sum, v plus u? Just connect these 2 points. Well, you get the same as u plus v, right? So, wow, so this is true. Vector addition is commutative. You can add the vectors in any order that you like. Okay. Now, I wonder if this is true, however. Well, you can answer it easily from the picture. What about the magnitude of u plus v? Is that going to be the same as the magnitude of u plus the magnitude of v? How can you tell that from the picture? So what's the magnitude of this resultant vector u plus v? That's this distance, right? That's this distance from here to here, the initial point to the terminal point. Would that be the same as adding these two distances together? The length of u and the length of v? Is that the same as following u and then following v? Are you going the same distance? No. Right, okay. This is shorter, right? Okay. U plus v has less magnitude than the magnitude of u plus the magnitude of v, right? Okay. Look like you're confused there. Did I?
6 on 7. 6 rather 0.
No, this is component form though, right? So why are you thinking this should be 0? Yeah, but in component form, you always assume that the origin is 0, 0, right? So you only write down, in effect, the terminal. Isn't this the terminal point? One of the sum here. There's the sum. 1, 2, 3, 4, 5, 6, right? And then 1, 2, 3, 4, 5, 6, 7. Yeah, okay. Yeah, so remember, component form different from, I don't know the name for the original form where you include both the initial point and the terminal. But this is false, okay? The magnitude of the sum is not the same as the sum of the magnitudes, okay? So you want to compute the magnitude of u plus v, you're going to have to calculate it separately, right? You can't just take the magnitude of u and add on the magnitude of v. Okay. So that's how you add vectors together. It's a very simple idea. Here it is in written out in words. Okay. So if you have two vectors, right, and you want to add them, the vector sum, or also called the resultant, okay, is the way you calculate that is just add the first components of your two vectors and the second components of your two vectors together. This is when your vectors are written in component form, though, right? When the vectors are written in component form with just the terminal point, the initial point is assumed to be 0, 0, right? You add the two vectors just by adding the two first components together and adding the two second components together. It's very simple. So vector addition is very straightforward if the vectors are in component form. Now, the other thing we want to learn here is what I just mentioned, right? How do we take a number, a scalar, a plain number, and multiply that times a vector? Well, that's also very easy too. Let's save that for next time, though. Okay, right? So we'll start our lecture next time with how do we take a number times a vector? But that's a very easy idea. Okay. Now, one of the things that's useful about that idea, though, is to help us understand what is the negative of a vector, right? So what if you take the negative of a vector? Because if you multiply a vector times -1, right? -1 is just a scalar number. Of course, that's going to give you the negative of the vector. So, so how do we calculate negative of a vector? What does it mean to put a minus in front of a vector? Okay, all right, but we'll save that for next time since we didn't get a break today. Let's stop a little bit early, okay? And do y'all have questions about anything? So you can keep your graph paper. We may use it again next time, so hang on to it, bring it back with you, all right? And just leave your name tit here. I didn't get a chance to address anyone by name, although I was talking to people. That was bad on my part. I'm out of practice, so try to fix that next time. Any questions? Any quick questions here? All right, so again, I'll post a video and the actual notes themselves, right? Filled out to this point, okay? And we'll continue working on these notes next time. We're almost through with this first set of notes. We're on starting on page 8. I think there's 10 pages there, so we don't have much left to go in our first set of notes. All right, guys, I will see y'all then. Take care until Wednesday.